surface area. We want to be able to compute the surface area for a double integral. Here's what we're looking at. Here, compute the surface area of a function. If you're given a function z equal to f of x, y, we want to compute here the area of the surface, the upper surface, or the outer rim of the solid. We compute that by looking at this area of S here, S here being the so-called solid, and we compute that based on one, R, the region down below, and then we compute what's really the arc length measure over the surface of each dimension, of each sliding rectangle, if you will. And you're looking at the so-called arc length, not of the rectangle, but of the edge of it. So we're computing this area on the surface, and we're taking all of these segments, these curvatures, these arc lengths, and then we're adding them up. Here's how the formula looks. This is the definition. This is what we'll be computing. The so-called surface area. Let S be the surface, not the solid. Excuse me. I'm thinking about the divergence theorem. So let S here be the represent the surface. So the surface area is said to be the double integral over R. So over here, the region, the base region, of ds. What is ds? ds is the change or the shift in the surface flow. Computed. Look at this. It's the square root of 1 plus the partial derivative of f with respect to x to be squared plus the partial derivative of f with respect to y to be squared dA. This square root is, my friends, this arc length, the arc length, not the arc length in the plane, but here, basically the arc length within the so-called space. And so that's what we're computing, and we get the so-called surface area. Well, let's look at some problems. Find the area of the surface. We're given z over the region. Some of these integrals are simpler in polar coordinates. How do you know when to use polar coordinates? If the region is given by a or as a circle or a part of a circle. Let's see if I can pinpoint that. This is a circle, so we're going to use polar coordinates. This is a square, do not use polar coordinates. This is a circle, right? So F here is inputted here, so here this circle in between 0 and 1. So we're going to use polar coordinates. So for this one, we don't have to. This is a square. So this is the region R. So R is defined 0 less than or equal to x less than or equal to 3, and then 0 less than or equal to y less than or equal to 3. So this surface area is the double integral over the region of ds, which this is the double integral over the region. This ds, this change in the surface, is broken down into two parts. What happens up top, which is the square root of 1 plus the partial of f with respect to x to be squared plus the partial of f with respect to y to be squared. Here's the second part, what happens downstairs in the region. So we have the area times its surface arc length. So you get the so-called surface area. So we break this down. So this is the integral from 0 to 3, the integral from 0 to 3 of the square root of 1 plus here f with respect to x is 2, right? The partial of f with respect to x is 2, and the partial of f with respect to y is negative 3. So we get 2 squared plus negative 3 squared, and this is a square, so it doesn't matter about dx, dy, or dy, dx, we get the same thing. So this is the square root of 1 plus 4 plus 9, so that's the square root of 14. Just put that out in the front. The integral from 0 to 3, the integral from 0 to 3, dx, dy. Integrate with respect to x. That's the square root. Thank you for telling me that. Don't want to lose that. The square root of 14 times the integral. Really, this is just 3 times 3, or the square root of 14 times 9. So this is 3 times the square root of 14, integral from 0 to 3 dy, and that gives us 3 times the square root of 14 times y evaluated from 0 to 3, and that's 9 times the square root of 14. And I think some of these integrals, if you see what's happening, you can just go ahead and just cut to the chase. Here, the region is a circle with a radius 3. It's the complete circle, so the region here, r goes from 0 to 3, and then theta goes from 0. It's the complete circle, 2 pi. And the good thing is that the partial of f with respect to x is equal to 2. It's a number, and the partial of f with respect to y is equal to negative 3. It's the number. So we get the same square root that we got before. So the surface area is this double integral from 0 to 3, 0 to 2 pi. That's a 2. Well, that funny rooster for the Frosted, is it Fruit Loops commercial? I don't know if he still comes on or not. It's the square root of the 1 plus the 2 squared plus the negative 3 squared. Looked like the same setup from the previous problem, but it's the square root of 14, right? 1 plus 2 squared plus negative 3 squared. Since we're converting to polar coordinates, this is r dr d theta. And I could use these numbers directly because the partial derivatives came out to be a constant. So here it's like I'm combining rectangular and polar form at the same time. And actually, I'm not here. What helps us with using this number and that number there, the 2 and the negative 3, is that when we did the partial derivative, the partial derivatives came out to be a constant. And so a constant is going to be a constant no matter where you are. So so we didn't have to convert. Typically, you convert this x to r cosine theta and this y to r sine theta, and you get a whole lot of stuff, and then you end up with the same thing right here. So this is just my little shortcut version that I use. This is a S. Okay. So the square root of 14 out in the front, the integral from 0 to 2 pi, integrate with respect to r, we get 1/2 r squared. R is evaluated from 0 to 3. Then d theta. So this is 9 over 2. So we have 9 over 2 times the square root of 14. The integral from 0 to 2 pi d theta. So this is 9 over 2 times the square root of 14 theta. Theta is evaluated from 0 to 2 pi. So your answer is 2 pi times 9 over 2 times the square root of 14, which is just 9 pi times the square root of 14. All right, the 2's cancel out. Let's see. Here, this region is a square. So here r is 0 less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 2. 2 does not like me. I don't like it. So this surface area is equal to the double integral here from 0 to 2, here from 0 to 2. We cannot convert to polar coordinates because the region is not defined in terms of some kind of circular flow. It's a square times the square root of 1 plus -2. 1 plus, take the partial of f with respect to x, we get -2x, and the partial of f with respect to y is 0. So this is -2x to be squared. Dag blasted, parentheses, 2x to be squared, dy dx. This is the integral from 0 to 2, integral from 0 to 2. This is the square root of 1 plus 1 Jake and Elwood Blues. This is 1 plus 4x squared dy dx. Why did I choose dy first? There's no y here, so let's integrate with respect to y, and that just becomes 2 times the single integral, right? 2 times the integral from 0 to 2 of the square root of 1 plus 4x squared dx. Now, this problem here is everything that you have learned, pretty much most everything you've learned from Calculus 2, right? So here use most of what you learn Calculus 2. Let's see. All right. The first thing that we're going to use is to convert this to trigonometric substitution. Well, here you have the forms a squared plus u squared. You use tangent theta. If it was a squared minus u squared, you use sine theta. And if it's a squared or u squared minus a squared, you use secant theta. So here's this plus. So we say let tan theta equal to 2x over 1. So here theta and tangent, opposite over the adjacent. Then the hypotenuse is that square root of 1 plus 4x squared. So if this is the case, then this implies, taking the derivative of both sides, that secant square theta d theta is equal to 2 dx. So 1/2 secant squared theta d theta is dx. So we represent this dx with this substitutionary form, trig substitutionary form. What about the square root? This looks like the square root is picked up by the sine or the cosine. Cosine theta, looking at the triangle, is 1 over the square root of 1 plus 4x squared. So you flip that, and that gives us secant theta is equal to the square root of 1 plus 4x squared. So we go back to the problem. The problem is 2 times the integral from 0 to 2. Is that right? Yes. The square root of 1 plus 4x squared dx. So this is 2 times the integral from 0 to 2. That square root becomes secant theta. And then the dx is 1/2 secant square theta d theta. So that's just the integral from 0 to 2 of secant. Leave it the way it is. Just get rid of the 2 and the 1/2. This is secant theta secant square theta d theta. Need to integrate. How do you integrate secant cubed theta? Well, we're going to use secant theta times secant square theta. Convert the secant square to 1 plus tan theta. It's the integral from 0 to 2 secant theta. Well, I guess I need you to see that this is secant cubed. You know it is. Let's just write it. Okay. So this is secant theta. The secant square is 1 plus tan squared theta d theta. We can write this as the integral from 0 to 2. I'm going to break this down. This is secant theta d theta plus the integral from 0 to 2 of secant theta tan squared theta d theta. Now the integral of secant theta is directly the natural log of absolute value of secant theta plus tan theta plus this integral from 0 to 2 of secant theta times tan squared theta d theta. On this part, we use integration by parts. So in doing that, let's see. It looks like if we let u equal to the tangent theta, then dv can represent secant tangent because the integral of secant tangent is secant. So that helps us out. So let's see if that'll work. Looking at these terms here. So let u equal to one of those tangents. And dv would be everything that's left, secant theta tan theta d theta. So here du is secant square theta d theta, and then v is the integral of this secant theta tan theta d theta, and that's just secant theta. So what we started with was the integral of secant cube. I'm going to put that here. This is the integral from 0 to 2. Told you everything, most everything you learned from calculus 2. This is here that natural log of the absolute value of secant theta plus tan theta, plus this integral of secant theta tangent square theta is broken up by the integration by parts. So we have uv, so it's plus uv, which is secant theta times tangent theta, minus the integral of v du. Right? The integral of u dv is uv minus the integral of v du. Right? The integration by parts formula. So this is minus the integral of u of v du, right? So which is secant theta times secant square theta. Right? See that? So you just multiply those. Secant cube theta d theta. So I want to put the initial starting ground that this was the integral of secant cube theta. So I'm going to add this secant cube theta to both sides, because there's no sense of us trying to compute this again, because we're going to get the same thing we just got through getting here. And if you do it again, you get the same thing. You have all these pieces and you have all these rounds. Well, somebody got to get smart to say, hey, this is a round, so I can take it from this part within the sum and somehow include it in what I'm looking for, and then divide out by the constant, and you get the result. So the whole of what I'm looking for, the sum, is calculated by actually what's inside of it, which is its strength. It's almost like saying that a person's children will sum up close to, maybe not all the time, who or what you are or what you represent. And that's just the philosophy of some mathematics. But anyway, I have 2 times the integral from 0 to 2. I'm adding the integral here of secant cube to both sides. You know, this is from 0 to 2 as well. Secant cube theta d theta. So this is the natural log of the absolute value of secant theta plus tan theta. Need to close that up. Plus secant theta tan theta. And everything there is evaluated from 0 to 2, not secant and tangent, not the thetas. We have to get back to x, and we'll get back to that in just a moment. So, but we were looking for this integral from 0 to 2, secant square theta d theta. This is 1/2 times the integral times the natural log of the absolute value of secant theta plus tan theta and plus secant theta tan theta. Evaluation from 0 to 2. Let's see. Go back to the triangle and let's see what was secant and what was tangent. Well, secant is that square root. See that? Secant theta is the square root, and then tangent is 2x. So that's what we need. So what we're looking for, this integral from 0 to 2 of secant square theta d theta is 1/2 times the natural log of absolute value of secant plus tangent. Well, tangent is the 2x plus secant is the square root of 1 plus 4x squared plus the secant times the tangent, that's plus 2x times the square root of 1 plus 4x squared. Now you can evaluate from 0 to 2. So this is 1/2 times the natural log. If we plug in x equal to 2, we get 4 plus the square root of 4 plus 4, 16 plus 1 is the square root of 17 plus 4 this is 1/2 times everything. Dag blasted. So this is 1/2 over 2 as well. So this is 2x, where x is 2, that's 4x. What am I doing? This is 4 times the square root, x is 2. The square root of 17, and that's over 2, which is just 2 times that. And then it's minus, you plug in x equal to 0, we get 0 here, we get the square root of 1, which is 1. The natural log of 1 is 0, and then here this gives us 0. So our answer is 1/2 the natural log of the absolute value of 4 plus the square root of 17, and this is just plus now 2 times the square root of 17. And had to be careful, I almost lost that 1/2 when we divided by the 2 here and also over there, right? So I put it there, saved myself. Good. Now, one more. Again, that previous problem, like I said, about a big chunk of what you learned in Calculus 2 can be found in that problem. Very good stuff. Number 11, not as cumbersome as the previous problem. It does involve, for the region, a circle aspect of it, and that's based on how f is defined. F is the square root of x squared plus y squared. So that x squared plus y squared does give us the circle. And so here we're going from 0 to 1. So the region is 0 less than or equal to r less than or equal, the radius is 1. And this is the complete circle. So it's 0 less than or equal to theta less than or equal to 2 pi. Okay, better. Now, the function, since we're converting to polar coordinates or cylindrical coordinates, f has to be redefined in terms of r and theta. And so x squared plus y squared is r squared. This is just r. So we're talking about the surface area of the partial of f with respect to r here, which is just 1. The partial of f with respect to theta, there is no angle, so it's 0. There's no angle in this formula. So the surface area, this double integral, we're going from 0 to 1 for r, and then 0 to 2 pi for theta. And this is the square root of 1 plus here, the partial of f with respect to r to be squared plus the partial of f with respect to theta to be squared times the r factor, remember that from the polar coordinates or the cylindrical coordinates, dr d theta. So this is the integral from 0 to 2 pi, the integral from 0 to 1. This is the square root of 1 plus 1 squared r dr d theta. So this is the square root of 2 out in front, the integral from 0 to 2 pi, the integral from 0 to 1 of r dr d theta. Integrate with respect to r, so we get 1/2 times the square root of 2 times the integral from 0 to 2 pi of r squared. R squared divided by 2, I just put the 1/2 there. Evaluate the r from 0 to 1. This is d theta. I'm not proud of the d theta. Well, a little bit better. So we evaluate the r from 0 to 1, just get 1. So here we have 1/2 times the square root of 2. There's no theta here, no sine, no cosine, so we just get the integral of this d theta is just theta evaluated from 0 to 2 pi, which is just 2 pi. And so our answer is pi times the square root of 2. Thank you.